The electrical grid spanning the globe relies on a highly efficient method of power distribution, alternating current, or AC. AC power is highly energetic and constantly in motion. It reverses directions dozens of times every second, creating a continuous, oscillating wave of electrical pressure. But the microscopic transistors inside computers, smartphones, and medical equipment cannot function on oscillating power. They require a stable, unidirectional flow of electrons, known as direct current, or DC. This results in a technical mismatch. The energy delivered by the wall outlet oscillates too rapidly for internal components that require a steady-state voltage to operate. Bridging this gap requires a mechanism that forces the wave to stop alternating and flow in one direction, a process known as rectification. As this diagram illustrates, the ultimate goal of rectification is to feed a volatile sine wave into a system and output a perfectly flat horizontal line of power. Accomplishing this requires arranging passive electronic components to physically manipulate the state of the wave and smooth out its time domain oscillations. Without this mechanical transformation happening in real time, no modern digital device could extract usable power from the grid. The first step in this transformation is isolating the circuit from the main grid and lowering the voltage to a safer level using a step-down transformer. Next, we introduce the critical component of rectification, the diode. Mechanically, a diode acts as a one-way valve, allowing electrons to pass through in only a single direction. This schematic shows the architecture of a basic half-wave rectifier. The lowered AC voltage from the transformer's secondary coil feeds directly into a single diode before reaching the load resistor. When the incoming alternating current swings into its positive half-cycle at node A, it pushes the diode into a forward-biased state. The one-way valve opens, and current successfully flows through the load. On our output graph, this flow registers as a positive hump of voltage. But when the grid power oscillating into its negative half-cycle, trying to push current backward, the diode becomes reverse-biased. The valve closes. The circuit is physically blocked, leaving a gap of 0 volts on the output. Because of this blocking action, the output signal frequency is identical to the input frequency. We get one positive pulse for every full AC cycle. While this circuit successfully forces the power to flow in only one direction, blocking the negative half of the wave means discarding exactly 50% of the input energy. This makes the topology unsuitable for efficient power supply design. To build a functional power supply, we need to recover that wasted 50% of the wave cycle without allowing any backward flow. The solution begins by changing the transformer topology. By tapping directly into the center of the secondary coil, we split the incoming voltage into 2 distinct phases. This diagram shows a full-wave rectifier. We now have a center tap establishing a 0-volt baseline with 2 separate diodes, D1 and D2, attached to opposite ends of the coil. During the first half of the cycle, the top of the coil is positive. Current flows through D1 and down through the load resistor, creating our first positive voltage peak. During the second half of the cycle, the voltage flips. D1 blocks, but now the bottom of the coil is positive. Current flows through D2 and down through the load resistor in the exact same direction as before. The negative wave has been physically inverted. Note the mathematical consequence written below the graphs. By utilizing both halves of the cycle, the output signal frequency is now double the input frequency. This doubling occurs because the dual diode architecture produces 2 distinct output peaks in the same span of time it takes the input wave to complete one cycle. By inverting the negative wave, we have successfully harvested all of the grid's available energy. However, while this power flows in only one direction, it is still pulsing from peak voltage down to 0. A voltage that rapidly drops to 0 volts and back up again is technically DC, but applying it to sensitive microelectronics would cause immediate system failure. The circuit needs a way to bridge the valleys between these voltage peaks, requiring a temporary energy reservoir. This final schematic reveals the solution. We add a capacitor, wired in parallel between the rectifier output and the load. As the rectified voltage rises toward its peak, the capacitor absorbs electrons, filling its internal reservoir with electrical charge. When the incoming voltage begins to drop, the capacitor releases its stored energy into the load. It physically props up the output voltage, bridging the gap before the next incoming wave can arrive. For this to work effectively, a specific engineering parameter must be met. As the note indicates, the value of the capacitor must be large enough to ensure a large time constant for the circuit. The time constant is the mathematical product of the load resistance and the capacitance. It dictates precisely how slowly the energy reservoir empties. If the time constant is too small, the capacitor drains too quickly, leaving unstable dips in the voltage. With a large time constant, the drain is slow, smoothing the output into a shallow ripple. Manipulating this time domain behavior is the final step. The capacitor ensures that the pulsing wave is smoothed into a steady flow of power. The conversion from grid power to device power requires overcoming a series of hurdles. First, a single diode enforces unidirectional flow but discards half the energy. Second, upgrading the transformer to a center tap topology inverts the negative cycle, doubling the frequency and recovering the lost power. Finally, adding a high-capacity filter manipulates the time domain, discharging stored energy to fill the voltage gaps. Looking at this progression, we can trace the raw input wave as it is chopped in half, fully inverted, and finally smoothed into a steady line of direct current. This conversion is achieved without digital logic or complex processing, relying instead on the passive physics of these few components. This sequence, transformation, full-wave rectification, and capacitive filtering, remains the foundational architecture inside almost every power supply operating today.